Yesterday, just past midnight in southern Italy, a magnitude 6.2 earthquake ruptured 150 miles below the surface at a depth where, by every conventional rule of how rock breaks, sudden, brittle failure should be physically impossible. No deaths, no damage, no tsunami. But seismographs in California, Alaska, and Japan all picked up the impulsive pulse within minutes. This is among the rarest classes of earthquake the planet ever produces. Only the second event of its kind from this exact region of Italy in over a century. By the end of this video, you will understand what just happened, why the textbook says it shouldn't have happened, and what comes next. Yesterday, at 12 minutes past midnight local time in southern Italy, the ground beneath the Calabrian coast moved. The rupture released roughly 6.3 times 10 to the 13th joules of seismic energy, the equivalent of about 15 kilotons of TNT, the yield of the bomb that destroyed Hiroshima. It registered as a magnitude 6.2 on the moment magnitude scale, after a brief upward initial estimate of 6.5 was revised by the European Mediterranean Seismological Center and the United States Geological Survey, working from the same waveforms. Nobody died, nothing fell down, no tsunami was issued. The pager alert from USGS came up green within minutes, meaning the model expects no fatalities and minimal economic damage. By the next morning, the news cycle had moved on. From the surface, this earthquake essentially did not happen. But this is among the rarest classes of earthquake the planet ever produces. And the reason no one was hurt is the same reason the event matters. The rupture occurred at a depth of 243 kilometers below the surface, 150 miles down. That depth is the entire story. At that depth, by every conventional rule of how rock behaves under stress, a sudden brittle fracture should not be physically possible. The pressure is too high, the clamp is too tight, and yet the rupture happened cleanly, sharply, with a signal so unambiguous that broadband seismographs in California, Alaska, and Japan all picked up the impulsive primary wave within minutes of arrival. Italy just gave geophysics one of the cleanest data points it has received all year on a problem that has been unsolved for almost exactly a century, the deep earthquake problem. And the textbook is, in some sense, we still cannot fully explain, wrong. To feel why the depth matters, you have to feel what the conditions are like down there. At 243 kilometers below the surface of the Earth, the pressure is approximately 7.5 gigapascals, about 70,000 atmospheres, or 70,000 times the air pressure you experienced when you stepped outside this morning. The temperature in the surrounding mantle is somewhere between 1,300 and 1,500 degrees Celsius. Under those conditions, the basic textbook says rock cannot fracture brittly, it can only flow. The same rule that lets glaciers move slowly downhill, viscous, plastic, gradual flow should govern any rock subjected to stress at that pressure and temperature combination. There should be no faults that can suddenly slip. There should be no earthquakes at all. The catch is that the rock at the hypocenter is not surrounding mantle. It is the cold interior of a subducting slab, a piece of old ocean floor that has been pulled down into the mantle and is colder than its surroundings, by maybe 400 to 600 degrees Celsius, because the slab has carried surface temperatures down with it as it descended. That thermal anomaly inside the slab is what makes brittle-like rupture even conceivable at this depth. But even with that cold slab anomaly, the confining pressure of 70,000 atmospheres should still pin every potential fault surface shut. The Coulomb friction model, the same equation that engineers use to predict rock failure on the surface, says the slip should not happen, and yet it happened. The fault inside the Ionian slab gave way. The radiated energy traveled outward through the mantle, took the textbook travel time, and arrived as a sharp impulsive pulse on broadband seismic stations on every continent. The rupture is real. The contradiction with the textbook is real. We are going to walk through one mechanism at a time, what scientists currently think might be going on inside that slab. The deep earthquake problem is not new. It is almost exactly 100 years old. In the 1920s, a Japanese seismologist named Kiyu Wadati noticed that earthquakes in Japan had different depths in different parts of the country. Shallow events near the Pacific coast, progressively deeper events as you moved inland, with the deepest events from hundreds of kilometers below the Sea of Japan. He had effectively mapped the descending slab beneath Japan decades before plate tectonics was a theory. In 1949, an American seismologist named Hugo Benioff generalized the observation. Working from a much larger global dataset, Benioff showed that essentially every major trench and arc system on Earth had the same inclined zone of seismicity, a dipping plane of earthquakes running from the surface trench all the way down to about 700 kilometers depth. The Aleutians, Japan, Tonga, the Andes, the Marianas, everywhere. The inclined zone became known as the Wadati-Benioff zone, and it became one of the most important early pieces of evidence for what we now call subduction. From the moment Benioff and Wadati mapped these zones, the central problem was obvious. Earthquakes at hundreds of kilometers depth should not happen. By every available theory of rock mechanics, the pressure is too high. The temperature, even inside a cold slab, should still favor plastic flow over brittle rupture. The fact that the deep earthquakes existed at all was a contradiction of the textbook understanding. Either the textbook was wrong, or something exotic was going on inside the descending slabs. 100 years later, we still cannot give you a clean answer. We have 3 candidate mechanisms, all of them with some laboratory support, all of them physically plausible, all of them with restricted depth and slab conditions where they should work. The argument among specialists is no longer whether deep earthquakes happen. The data settled that question decades ago. The argument is what specific mechanism drives any specific event. The Italy rupture of June 1st is the latest test case. The first candidate is called transformational faulting in metastable olivine. The mineral olivine, the dominant component of oceanic mantle, and therefore of subducting slabs, should transform into denser polymorphs at depths around 410 kilometers and again at 520 kilometers. But because the slab interior is cold, the transformation can be kinetically delayed. Metastable olivine can persist much deeper than it should. When it eventually does transform, it can do so suddenly along narrow zones, releasing energy that looks, from the outside, exactly like a brittle earthquake. Harry Green and Pamela Burnley laid this mechanism out in Nature in 1989 and reproduced it in the lab. It explains the deepest deep events well. It is harder to apply at the shallower end of the deep zone, including the 243-kilometer Italy event, because at this depth, ordinary olivine is supposed to be the thermodynamically stable form. The second candidate is called dehydration embrittlement. Subducting oceanic lithosphere carries water down into the mantle, not as liquid, but chemically bound into hydrous minerals like serpentinite, which can lock up to 13% of its weight as water in its crystal structure. As the slab descends and heats up, these hydrous minerals decompose, releasing the water. In a confined volume, the released water builds up local fluid pressure. If the fluid pressure rises high enough to approach the surrounding lithostatic confining pressure, the effective stress on any potential fault surface drops to near zero. The fault, which had been pinned shut, becomes free to slip. Steve Kirby developed this framework at USGS in the mid-1990s. For an event at 243 kilometers, in a cold slab carrying antigorite serpentinite, dehydration embrittlement is one of the strongest mechanism candidates. The Italy event sits within the depth range where this mechanism should be active. The third candidate is called thermal shear instability. The physics is simple. Any region of stressed rock that starts to shear generates heat. The heat lowers the local viscosity. The lower viscosity allows more shear, which generates more heat, which lowers viscosity further, which produces more shear. The positive feedback can run away into a self-sustained slip pulse that propagates through the rock at velocities comparable to seismic wave speeds. From the outside, it looks identical to a brittle earthquake. Bruce Hobbs and Alison Ord proposed this mechanism in the late 1980s. Stefan Break and Yuri Podlachikov refined it in Physical Review letters in 2007. The strength of this model is that it does not require any special mineralogy. It can in principle work at any depth, in any slab. The weakness is that quantitative predictions about when and where it will operate depend on parameters that are hard to measure in the laboratory. The current consensus among specialists is that all three mechanisms probably operate in different proportions, at different depths, in different slabs. The Italy event of June 1st could plausibly involve any of them, or some combination. The detailed source analysis that INGV, USGS, and the Harvard Global CMT Group will produce over the coming months will give some hints, particularly through corner frequency analysis of the impulsive teleseismic pulse, but a definitive answer for this specific event is unlikely. The puzzle stays open. To understand why this earthquake happened, where it happened, you need to understand a piece of geology that almost nobody outside specialty geophysics ever thinks about. It is called the Calabrian Arc, and it is the surface expression of one of the most active small subduction zones on the planet. Under the southern Tyrrhenian Sea, a finger of old African oceanic lithosphere, a piece of Mesozoic Ionian sea floor, more than 150 million years old in places, has been pulled down beneath the Eurasian plate, along a steeply dipping plane. The slab is narrow, perhaps 200 kilometers wide, descending at angles approaching 80 degrees in its deepest portions. Seismic tomography has traced it all the way down to about 700 kilometers depth. The Italy rupture of June first sat squarely inside the deepest portion of this slab. The Calabrian slab is in active rollback. The trench is migrating southeastward through the mantle, away from the Italian peninsula, at rates of 2 to 5 centimeters per year, faster than the African plate is converging with Europe. The slab is essentially sinking under its own weight faster than it is being fed from the surface. As it rolls back, the upper plate is stretched and pulled apart, opening the Tyrrhenian Backarc Basin, the body of water between Italy and Sardinia, which is, geologically, a brand new ocean basin only a few million years old. The same slab feeds Mount Etna, Stromboli, and Vulcano. As the slab descends and heats up, it releases water into the overlying mantle wedge. The water lowers the melting point of the mantle. The mantle partially melts. The melt rises through the crust and erupts at the surface. Etna gets its magma, ultimately, from this exact process. Stromboli does too. So does every other volcano in the Aeolian chain. What this means is that the Italy deep earthquake of June 1st and the ongoing eruptive activity at Etna are signatures of the same geophysical object. The slab is alive. It is moving. It is releasing fluid and partially melting the rock above it. And once in a century or so, somewhere inside its descending body, a piece of it ruptures cleanly, releases a few times 10 to the 13th joules of energy, and sends an impulsive pulse to seismographs all over the planet. The slab moved last night. The slab is going to keep moving. Before we go further, the rarity has to be put in perspective. Globally, earthquakes of magnitude 6 or greater at depths of 200 kilometers or more occur approximately 5 to 8 times per year, total, planet-wide. They are concentrated in a small number of regions: Tonga and Fiji, the Vanuatu Arc, the Marianas, the Java Banda Sea, the Sea of Okhotsk, the Bucaramanga Nest beneath Colombia, and the Hindu Kush. The Calabrian Arc is the smallest and rarest member of that set. In the entire instrumental record of seismology, the southern Tyrrhenian deep focus zone has produced exactly one previous event of comparable magnitude and depth. That event was in 1915, 111 years ago. Modern catalog reanalyses place the 1915 event at a depth somewhere between 200 and 300 kilometers, with a magnitude estimated between 6.7 and 7.0. Slightly larger than the Italy event of June 1st, and roughly the same depth. The same slab, the same region, the same kind of rupture. Between 1915 and 2026, a span of 111 years, the Calabrian deep zone has been essentially silent at this magnitude class. The June 1st event is the second entry in a 2-event catalog. That is how rare we are talking about. What does that tell us, statistically? Honestly, not much. With only 2 data points separated by a century, you cannot compute a recurrence interval. You cannot estimate when the third event will arrive. You cannot say whether the typical pacing is 60 years or 200 years or 500 years. The data is too sparse. What you can say is that this is a real, recurring phenomenon. The slab does produce events of this size and depth, occasionally, and that the recurrence interval is somewhere on the order of decades to centuries. The third event will come. We do not know when. In the hours after a notable earthquake, especially one with an unusual feature like the depth here, a series of online claims tend to attach themselves to the story. The most common one is the claim that a deep event of this size is a precursor to a much larger, shallow event somewhere else in southern Italy. The claim does not survive the seismological literature. The Coulomb stress transfer framework, established by Jeffrey King, Ross Stein, and Jian Lin in a foundational 1994 paper, lets you calculate how much stress change a given earthquake produces on a given target fault. For an event at 243 kilometers depth, the calculated stress change at any potential shallow target fault in the southern Italian crust is less than 0.1 bar, about the same magnitude as daily variations in atmospheric pressure, or about 10% of the stress change produced by ocean tides. The number is far below the threshold that would measurably change shallow earthquake probabilities. The deep event, mechanically, does not load the surface faults. The historical record confirms this. The 1908 Messina disaster, Italy's worst recorded earthquake disaster, with over 75,000 fatalities, had no deep focus precursor. The 1980 Irpinia earthquake had no deep focus precursor. The 2009 L'Aquila earthquake had no deep focus precursor. Crustal earthquakes in Italy happen on their own stress budgets, on faults that operate independent of what is happening 243 kilometers below them. Italy's shallow crustal hazard is exactly what it was the day before the deep event: high, persistent, and unchanged. The other claim worth addressing is the suggestion that the global seismograph detection, the fact that stations in California, Alaska, and Japan all picked up the impulsive pulse, is somehow unusual. It is not. Every earthquake of magnitude 6 or greater anywhere on Earth is recorded on every operational broadband seismograph on the planet. The global detection is the baseline. What is genuinely distinctive about the Italy event is the impulsiveness, the sharp, fast-rising shape of the recorded pulse, which is the textbook signature of a deep focus rupture. The recording station saw exactly what the physics predicts. There is no anomaly in the detection itself. The anomaly is in the rupture mechanism, and that anomaly is exactly the one the deep earthquake problem has been trying to explain for the past century. In the next few weeks, INGV in Rome, USGS NEIC in Golden, Colorado, and the Harvard Global CMT Group will complete detailed source analyses of the June 1st event. They will produce refined moment tensor solutions, corner frequency estimates, stress drop calculations, and a careful comparison with the catalog of other deep focus events from around the world. Some of that work will be public within days. Some will appear in peer-reviewed journals over the coming year. The big question that analysis cannot answer is which of the 3 candidate mechanisms drove the rupture. The source analysis tools we have are not quite precise enough, even with modern instrumentation, to definitively distinguish transformational faulting from dehydration embrittlement from thermal shear instability. The Italy event will become one more entry in the catalog of deep focus earthquakes that future mechanism research will use to try to nail down which physics dominates under which conditions. The science moves forward incrementally. This is one increment. In the broader operational sense, there are a few things to watch over the next 12 to 24 months. First, any additional deep events from the same slab, second or third events at similar depth, would suggest that the slab is going through a phase of accelerated internal deformation, which would be a more interesting story than a single isolated rupture. Second, any unusual behavior at Etna, Stromboli, or Volcano. The slab feeds those volcanoes, and any change in the slab's internal mechanics could in principle eventually express itself at the surface. Third, the routine continued background seismicity of the Calabrian crustal system, which will produce events of various sizes on its own schedule, independent of the deep slab. What is not going to happen, as far as the seismological evidence supports it, is a sudden surface earthquake triggered by the deep event. Italy's crustal hazard is what it has been for centuries. The deep event does not change it. If a damaging shallow earthquake happens in southern Italy in the coming weeks, it will be on its own clock, not the deep slabs. There is also a quieter but worth noting question about whether the slab's behavior is changing on a longer timescale than the routine rollback rate suggests. The Calabrian arc has been rolling back for tens of millions of years, but the rollback has not been uniform. There have been faster phases and slower phases, episodes of slab tearing and slab acceleration, periods of more intense volcanism at the surface, periods of less. The Italy event of June 1st does not, by itself, tell us whether we are in one of those phases or in routine background activity. It will take additional data, additional deep events, GPS deformation measurements, changes in Etna's eruption rate, or in the regional seismic moment release, to know whether the slab is doing something unusual or just doing what it always does, very rarely, on a centennial schedule. In the meantime, the analytical project that the June 1st event launches will run for years. The waveform data is high quality. The global station coverage was good. The depth is well constrained between USGS and EMSC independent solutions. The Italy event will, over time, become one of the better characterized recent deep focus earthquakes in the catalog. That alone, regardless of damage or news cycle attention, makes it worth taking seriously. The single most important thing to take from this event is the contradiction itself. A magnitude 6.2 earthquake at 243 kilometers depth is, by the textbook understanding of how rock breaks, supposed to be impossible. It happened anyway. The textbook has been incomplete on this question for a century, and the Italy event of June 1st is one more piece of evidence that the question of how rock fails at the depths where conventional brittle failure should be prevented is still open. The science is not closed. The puzzle is not solved. And every rare event like this one is one more data point that, slowly, the field is using to work toward an answer. We will keep watching.